Hi everybody, this is section 11.3. We're in the middle of the last chapter. We're going to investigate logarithms today. So again, this is a real brief skimming. There's 17 points in this, but there's so many that are so easy and quick that the first 8 they're all the same, so they should go very, very fast. Okay, so what is a log? Well, a log is an inverse of an exponential. So what does that mean? Okay, well, what's an inverse? First of all, we skipped the inverse section on this, but you already know what inverses are. If I take a number and add 2 to it, the inverse, or how I get back to the original number, would be to subtract 2 from it, right? Like take this answer, whatever that is, and subtract 2. So addition and subtraction are inverses of each other. So is multiplication and division, right? Those are inverses of each other. If I double something and then take that answer and divide it in half, I get back to my original number. Square roots and squares, things like that. You know, if I square root something and then square it, I get back to my original number. Well, exponentials and logs are also like that. So we need some sort of an exponential logarithmic equivalency. So just like what we had with radicals, and I'm going to put this one down because we're going to need it in this section. Remember that these were the same. Okay? This is the same thing, only just a different form. We also have log, let's see, b to the c equals a. And that's equivalent to b to the a is c. Okay? What is a logarithm? Well, a logarithm, without having the use of calculus, I can't really explain what a logarithm is or what a logarithm really does. And so right now, just think of it as a function, just like any other function, whether it's a quadratic function, an exponential function, whatever you have. We can also have logarithmic functions. We have 2 types of logs. We have a common log, which is the base is 10 here, okay? And when we write those, we don't even write the base 10 in there. We just leave it out. So this is called a common log, okay? We have a common log button right here, all right? And then we have a natural log, which is a base of e. And again, they're so common and so used that we don't write the e in there. We just write ln x, and we assume that this has got a base of 10. This has a base of e, so this is a natural log. And we have a natural log button right here. Okay. E is a number like pi. E is 2.7. Just like pi, it's got, you know, special properties and things like that. Otherwise, like on this problem right here, we have a base of 5, and we don't have a base 5 button, so we could never punch that into our calculator. All right? So what we're going to do in these first 8, we're going to go back and forth between these 2 forms. That's all we're going to do right now. All right? So let's take a look at what we have there. We have 5 to the 5th power, right underneath this one, is equal to 3125. Now that's got to be a true statement, okay, to start out with. So let's just, you know, verify, yeah, that 5 to the 5th power is 3125. All right. Now, to express that in a logarithmic form, we just take these letters. B is 5, right? A is 5, and C is 3125. So I'm just going to rewrite it this way. So I'm going to say that the log base 5 of C, okay, C is 3125, is equal to 5, which is A. Okay? You'll get into more what a log is when you hit college algebra, sort of, and then if you keep going onto pre-calc and calculus and things like that, you'll really see the usefulness of logs. Right now, they're just used to solve exponentials. If we get stuck exponentially, we switch it to a logarithmic form and we can solve, or vice versa. If we get stuck logarithmically, we can switch it over to an exponential and solve. So it's hard to grasp what a log is, and I'm not going to try to get into that. So just, I guess, go with it, right? Same thing here. Okay. Now, one stipulation that I didn't write down right here that we're going to need is that b has to be bigger than 0 and b can't be 1. Okay, so the base here, this base right here, has to be a positive number, and it can't be 1 because 1 raised to any power is 1. It's just boring. All right, we can't take logarithmically. We can't take the log of a negative base. So here's my two stipulations. Okay, so here's my natural common logs. I know that the b has to be positive and not equal to 1, and here's my conversion. So again, I'm going to put this over here. I've got 1/5 to the negative 3 power is equal to 125, which is a true statement. So b is 1/5, a is negative 3, and c is 125. So it's super easy to change these over. We're going to take the log of a 1/5 power to the c, which is 125, right, is equal to negative 3. Okay? So these are just switching forms. Is negative 3. All right. I will not do that one. It's exactly the same. All right, so here we're going to need to, here we have a radical, and I have no conversion between radicals and logarithms, but I do have radical to exponential and then exponential to logarithm. So that's what I'm going to do here, okay? So I'm going to take the cube root of 64 and turn that into a exponential. There's a 1 there, so this is 64 to the 1/3 power is equal to 4. Okay, and then proceed from there. All right, super easy again. All right, so let's go the other way. All right, so the other way is taking something that looks like this and turning it into an exponential, right? So here it says to take, I'm going to switch these around so it follows this, all right? I've got log base 5 of 5 is equal to 1. I can always just flip-flop these on each side. So here b is 5, c is 5, and a is 1. So that's the same thing as 5 to the first power is 5. Now a lot of these over here you can't check. Okay, you don't know whether this is true or not because we don't have a base 5 or a base 1/5 button. But when I'm going from logarithmic over to exponential, I sure can check those. Is 5 to the first power equal to 5? Well, yeah, it sure is. Okay, so that's why we want to make sure that when we can check these, we will check these. Okay, I will show you a way of checking these because there's always a way to check everything. I'll show you those later. But right now we don't need that. All right, so here we have b to the, what did I say that was? B to the a. B to the a is equal to c. This is multiple choice here, so it's super easy. All right, so it'd be 10 to the negative 2 power is equal to 1 over 100. That's this one, right? I'll show you all the options here. This to this power is equal to that. That is this one right here. Good job. Okay, oh, let's check it. Here I just went off on checking it. You know, in a test situation, you would want to make sure that you have the right answer. Yes, of course it is. Okay? 3 to the 0 power is 1, right? That's what that says. 3 to the 0 power is 1. Is it? Yep. So there's your equivalency. Check them when you can. And oops, oopie. Let's see what we got going on here. 36 to the 1/2 power is 6, right? 36 to the 1/2 power. Now what is the 1/2 power? That's the square root. If I was to turn that into a radical, we know the square root of 36 is 6. We also know 36 raised to the 1/2 power is 6. Okay, so that's what you would put in here. Okay, 36 to the 1, well, here, let's just do it. 36 raised to the 1/2 power is equal to 6, right? Good job. Okay, so you have to put the whole thing in there. All right, so that's what the first 8 problems are, is just getting used to the changing forms of these types super fast, super easy, all right? Now we're gonna solve, we're gonna start solving. Now, whenever I'm stuck as a logarithm, I change it over to an exponential form and I try to solve it that way. And whenever I'm stuck exponentially, I'm going to try to switch it over to a log form and solve it that way. So you can see right now that I'm stuck. I don't have a base 4 button, right? Do I have a base 4 button? No, I don't. I only have a base 10 and a base E. Okay, so anytime that I have anything else, I can't use my calculator. So what do? Well, let's see here. All right, I want to go from my logarithmic form to an exponential form, so I'm going to convert it using 4 to the x power is 8. All right, 4 to the x power is 8. That's the conversion. All right, if that confused you, which I'm thinking it might have, because, okay, so this was log base b of c is equal to a. Just switch those so that it looks more like that. And then you can see b is 4, c is 8, a is x, and then we're going back to the b to the a is c. Right, these are equivalent. So b to the a is c, 4 to the x is 8. That's where I got that from. Now I don't know what that is, right? I have no idea. 4 to the x power, 4 to the first power is 4, right? 4 to the first power is 4. 4 to the second power is 16. So I'm somewhere in between there, right? How do I get 4 raised to some power is 8? I don't. Not a nice whole number anyway. So what I'm going to do is I'm going to look to see at the 4 and the 8 if I can't rewrite those as a exponential with the same base. Well, I can't write an 8 with a 4, right? I can't raise 4 to any power to get an 8, but I can write 2's raised to certain powers and get a 4 and an 8. Okay, so I kind of use my logic skills and I say there's a base of a 4, a base of a 2 in a 4 and an 8. Okay? 4 is 2 squared and 8 is 2 cubed. See how my base is the same then? So I'm going to rewrite these as 2 squared raised to the x power is equal to 2 cubed. All right, now I know I'm going to go back to my exponential rules, that when I have a power raised to another power, it's multiplication. So here we have 2 to the 2x power is equal to 2 cubed. Okay? Now I have 2 raised to some power has to equal 2 raised to another power. So therefore, if these are the same, then these have to be the same. So therefore, 2x has to equal 3. All right, so I just take these powers. Once my bases are the same, these two pieces have to be identical, otherwise it's not equal to each other. This is easily solved. Divide by 2, divide by 2, so x is 3/2. Which makes sense because it had to be between 1 and 2. 1 only got me to 4, 2 got me to 16, so it had to be a number in between 1 and 2, and it's 1/2. Okay? This one wants the fractional form, so I'm going to put 1/2 in there. But I'm going to, first of all, raise 4. Well, I should check it here. To the 3 divided by 2 power, and see if indeed I do get 8. And I do. Okay, 3/2. Excellent. Okay, I've got log base x of 2 is 1/2. I can't do this in my calculator because I don't have a base x button, right? So I'm just going to switch it over to an exponential right away. X to the 1/2 is 2. X to the 1/2 is 2. Okay? Now how do I get rid of a 1/2 power? Well, let's just take a look. Let's go backwards just a bit in our math knowledge. Let's say that I wanted to do, get rid of a square. Well, let's not do a 5. What if I wanted to solve for an x squared equals something? Well, I would take the square root because those are opposites, right? They're inverses of each other. All right? And the reason that is because if I take x squared and I raise it to the 1/2 power, which is really the square root, isn't 2 times 1/2 1? Isn't this x? Okay, so I always want to turn this exponentially into a 1. Well, so I'm going to do that here. I'm going to say I want to get rid of my 1/2. So in order to do that, I have to square it, right? Because 2 times 1/2 is 1. Whatever I do to one side of the equation, I have to do the same to the other. Always. That's your golden rule of algebra. So x to the 1/2 power squared, let's just put a number in there and just try a 5. Okay, so if I had 5 raised to the, let's start over, parentheses, 5 raised to the 1/2 power, and then I'm going to square that, the whole thing, I get back to a 5. That's what I want, like the 5's the x. Okay, so 1/2 and 2 are inverses of each other when I raise them. So here we have just x on this side, and we have 2 squared, which is 4 on that side. Okay, so we would have log base 4 of 2 is equal to 1/2. Well, is that a true statement? Can't check it this way, but turn it into an exponential. 4 to the 1/2 power is 2. Is that true? Right? This raised to that power is this. Well, let's try it. 4 raised to the, no, raised to the 1/2 power is indeed 2. Okay? So your solution set is indeed 4. So at least you can check it exponentially. Okay? Let's try another one. I don't know how many of these I'm going to do. I think they're all done the same. Log base x of 16 is equal to -4. Okay. I don't know how to do this logarithmically, so I'm going to change it into an exponential. X to the -4 power is 16. X to the -4 power is 16. Okay. How do I get rid of a -4? Well, I want to turn that into a 1, right? So -4 times a -1/4 will give me what? Well, negative times a negative is a positive. That's good. And 4 times a 4th is 1. All right, good. So I'm going to take each side and raise it to the -1/4 power. I can do anything I want to either side, as long as it's done to both. So -4 times -1/4 is just 1, which is x. And let's just be, since we're at the end of the semester here, let's just be lazy. 16 raised to the -1. I've been lazy all semester. Let's admit it. Let's just admit it, Simone. 0.5 or 1/2. I don't know what it wants. Fraction. Okay. So we have 1/2 on that. All right. We don't have a log base 20 button, so we are going to turn that into an exponential. 20 to the 0 power is x. 20 to the 0 power is x. What is anything to the 0 power? It's 1. It doesn't matter what it is. My dog's face raised to the 0 power is 1. So the solution set is 1. All right. This is an interesting question here. All right. Solve the following equation for s. Well, all we have here is s to the, let's look at it logarithmically, do exponentially. Let's change it over. S of s equals 1. So that means s to the first power is s. S to the first power is s. Well, what could we put inside of that for an s? Well, I can put in anything that I want. I can put a 5 to the first power is 5. I can put in a -1/2 to the first power is -1/2. Anything raised to the first power is itself. So basically, this is anything. I can put whatever I want in there and it's going to work. But what are my restrictions on my base, my b, which happens to be my s? Has to be a positive number, and it can't be 1. So that's the one that we're going to look for. S has to be positive. Well, first of all, just based on this, it could be anything. But then as far as a logarithm goes, restrictions, it has to be positive and it can't be 1. So that's the one that you want there. Okay? It's kind of a silly question. You're just going to get one like that and it's the same. But it just shows you why we need that extra definition. All right, so let's go back to solving. Do I have any room? Not much. Alrighty, I've got log base x to the 1/64th is equal to -3. Can't do anything logarithmically, so I'm going to change it to x to the -3 power is equal to 1/64th. Got to get this into a 1. I'm going to raise each side to a -1/3 power, because -3 times -1/3, -3 times -1/3 is 1. And x to the first power is x. If I do that to this side, I have to do it to this side. 1/64th raised to the -1/3 power. So this is x. And just use your calculator. 1/64th raised to the -1/3 power is 4. Okay? We've only got 3 left. Let's see. I don't want to leave you hanging at the very last sections here. All right, let's try this one. We've got log base 16 of 8 is x. Can't do anything with that as a log, so I'm going to say 16 to the x power is 8. Okay, now we're back to these similar bases. I have to get a similar base in order to set my exponents equal to each other. I can't write them in terms of 16s or 8s, but I can write them in terms, I can't even do in 4s. There isn't a base of a 4 and an 8 as far as a power goes, right? 4 raised to some power is never going to be 8. Well, 3/2 it is, because we just did that one, but we don't know that. Let's pretend we don't know that. So we're going to say, well, I know that I can write a 16 and an 8 with 2's, right? So 2 cubed is 8, and 2 to the 4th is 16. I'm trying to get these bases the same. Okay, so let's going back to that other problem. So here we have 2 to the 4th raised to the x power is equal to 2 cubed. Powers of powers is multiplication, so I have 2 to the 4x is equal to 2 cubed. Now my bases are the same, so I can set my exponents to be equal to each other as well. Okay, so 4x equals 3, dividing 3 by 4 gives me 3/4. So 16 raised to the 3/4 power. This part I can check. I can't check with the other one yet. 3/4 power. Yep, it's 8. So that works right there. So this will be 3/4. Okay. Does that one look scary? This one's, I almost took it out because it was too easy. It looks really bad as a log. I look at this and I go, what the heck? I don't even have a log base pi. I have to take pi to the 10th power. It's a nightmare. But really, is it? Not really. Not when you look at it exponentially. We have pi to the x is this. So we have pi to the x is pi to the 10th. Well, that's so easy that it's just ridiculous. X has to be 10, right? The only thing that's going to make that true is pi to the 10th is pi to the 10th. So x has to be 10. So even though that looks really nasty, it's easier than the other ones. All right, one more, and then I'm going to stop yip-yapping here. Just think about it. You're going to have to not listen to me for the rest of your lives. How nice is that? All right, so we have 4 to the x is the square root of 64. 4 to the x is the square root of 64. Well, I can turn this into a exponential, or I can actually evaluate it. So 4 to the x is 8. Didn't we already do that one? Wasn't it 3 halves? I think this is the same darn problem. Should have taken this one out too. Wasn't it 8? Yeah, 3 halves. Okay. What's going on? Hello? There we go. All right. And that's it. So quick and easy. We're going to look at properties of logarithms next. And they have all kinds of different kinds of properties, and we're going to start evaluating them and solving. So I will see you for the next couple sections. Take care.